Imagine standing on a Martian plain, feeling a warm breeze, watching trees sway gently. A blue sky above, clouds drifting lazily past. Sounds like pure science fiction, does it not? But for decades, humanity has dreamed of terraforming Mars, transforming it into a second Earth. We have seen the breathtaking art, read the visionary novels, and felt the primal pull of a future among the stars. However, the vast majority of what you believe about turning Mars green ... is probably wrong. The challenges are not just immense, they are fundamentally different from what most people understand. And the path forward, if one even exists, will redefine our place in the cosmos in ways you cannot possibly predict. You are not alone in wondering if we can truly make Mars habitable. The idea itself sparks wonder, urgency, and for some, a touch of desperation. But beneath the inspiring headlines and dazzling concept art lies a bedrock of scientific realities that make this dream almost impossibly complex. Here at SpaceRepo, we are going to peel back the layers of popular imagination and scientific aspiration. We will show you precisely what it would take, what we are truly up against, and whether humanity possesses the power to rewrite a planet's destiny. So, what does terraforming actually mean? It is not just about planting a few seeds. It is the hypothetical process of deliberately modifying a planet, moon, or other body to make it capable of supporting Earth-like life, specifically human habitation. This concept took root in the human imagination long ago, gaining serious scientific traction in the mid-20th century. Think of visionaries like Carl Sagan, who in the 1970s proposed melting the Martian polar ice caps to thicken the atmosphere. Or imagine the contemporary plans that involve gigantic orbital mirrors, redirecting sunlight to warm the planet's surface. The ambition here is staggering. We are talking about altering the fundamental properties of an entire world. The temperature, the atmospheric pressure, the very air we breathe, the presence of stable liquid water, all would need to be engineered from scratch. This is not just a colossal engineering project. It is planetary-scale alchemy. Before we can even think about adding an atmosphere, we must understand why Mars does not have one today. Around 4 billion years ago, Mars was a very different place. Data from the Perseverance rover and other missions show clear evidence of ancient riverbeds, lakes, and oceans. Mars was wet and, potentially, warm, a stark contrast to its arid state now. What happened? The key difference between ancient Mars and Earth lies deep within their cores. Earth has a powerful global magnetic field generated by its molten iron core. This magnetic field acts like a planetary shield, deflecting harmful solar winds, continuous streams of energized particles constantly blasted from the sun. Mars, being smaller, cooled much faster than Earth. Its internal dynamo, which generates a magnetic field, largely shut down around 3.8 billion years ago. Without this protective shield, the solar wind began to relentlessly strip away Mars's atmosphere, molecule by molecule, over millions of years. This is not speculation. Measurements from the MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission have directly observed this atmospheric loss in action. So even if we added an atmosphere without a global magnetic field, it would simply be blown away again. This is not a leaking faucet. It is a planet-sized hole in the cosmic bucket that we would need to plug permanently. Okay, so we need an atmosphere, and we need to protect it. Let us ignore the magnetic field problem for a moment and focus on the initial warming. The most commonly proposed methods center on releasing massive amounts of greenhouse gases into the Martian atmosphere. Mars has plenty of frozen carbon dioxide in its polar caps and locked within its regolith, the loose surface material. One idea involves detonating nuclear weapons at the poles to release this carbon dioxide. Another, more gentle approach suggests large orbital mirrors or vast arrays of solar sails. These would focus sunlight onto the polar caps, sublimating the frozen carbon dioxide and water ice, thereby thickening the atmosphere and initiating a runaway greenhouse effect. This sounds plausible, does it not? However, the numbers are daunting. Even if we released all the accessible carbon dioxide, it would only create an atmospheric pressure equivalent to about 7% of Earth's barely enough to walk around without a pressure suit, and nowhere near what is needed for liquid water to be stable on the surface. We would need to introduce additional, much more powerful greenhouse gases like PFCs or perfluorocarbons. Manufacturing these on the scale required, transporting them, and distributing them across an entire planet would be an undertaking far beyond any industrial effort in human history. This would mean launching hundreds of thousands, or even millions, of rockets, each carrying payloads of these potent chemicals, a truly staggering logistics challenge. Even if we cracked the atmosphere and temperature, the challenges do not end there. Consider radiation. Without a thick atmosphere and a global magnetic field, Mars is bathed in dangerous cosmic and solar radiation. This radiation, including galactic cosmic rays and sudden solar particle events, would sterilize the surface, making it incredibly difficult for complex life, including humans, to thrive without extensive, permanent shielding. To survive, you would effectively be living underground or in massive radiation-proof habitats that resemble fortified bunkers, not open plains. Then there is the soil itself. Martian soil contains high concentrations of perchlorates. These are toxic to humans and many plants, interfering with thyroid function and posing a serious health risk. Removing or neutralizing these contaminants across an entire planet's surface would be another Herculean task, far more complex and costly than any land remediation efforts on Earth. It would be an environmental cleanup on a planetary scale. And water. While Mars has ice, it does not have a deep, active water cycle like Earth's. We do not just need water, we need precipitation, rivers, oceans, and the complex geological processes that maintain them. Creating a global hydrological cycle from scratch, sustaining it, and ensuring it can support a functioning ecosystem would take millions of years, not mere decades or centuries, even with the most advanced technology. So, where does this leave us? The technical hurdles are monumental, requiring energy, resources, and timeframes that currently stretch far beyond our capabilities. Data from the late 2010s and early 2020s suggests that the amount of easily accessible carbon dioxide on Earth is simply insufficient to create a breathable atmosphere, even with maximum effort. It is like trying to fill a swimming pool with a teacup. But there are also profound ethical questions. Is it right to fundamentally alter another celestial body? What if Mars harbors subsurface microbial life perfectly adapted to its current harsh conditions? Our terraforming efforts could irrevocably destroy such life, extinguishing an entire branch on the tree of existence before we even understood it. This concept is called planetary protection, and it is a core tenet of responsible space exploration. And then there is the economic reality. Estimates for terraforming Mars range into the quadrillions of dollars, spanning centuries. Imagine if even a fraction of that investment, that collective human effort, was directed towards solving the very real, very pressing environmental crises on our own planet. Is terraforming Mars truly an escape from our terrestrial problems, or merely a monumental distraction from our most immediate responsibilities right here on Earth? So, can we terraform Mars? The short scientific answer right now is probably not. At least not in any time frame relevant to human lifespans, and certainly not with current or even near-future technology. The dream of a blue Mars is intoxicating, but the reality is a stark reminder of the unique, delicate miracle that is Earth. This does not mean we should abandon Mars. Far from it. We should explore it, understand it, and perhaps even establish scientific outposts and research colonies. But building breathable domes and underground cities, adapting ourselves to Mars appears far more feasible than adapting Mars to us. Understanding the immense difficulty of terraforming Mars gives U.S. profound perspective on the preciousness of our own living world and the incredible complexity of planetary scale engineering. It compels us to cherish and protect the one truly habitable world we already possess. What are your thoughts on terraforming Mars now? Does knowing the full scientific reality change your perspective on humanity's future in space? Share your most surprising takeaway or your own ideas in the comments below. Your insights help us all expand our understanding. And if you are fascinated by the real science behind our cosmic ambitions, be sure to hit that subscribe button for SpaceRepo. We are here to navigate the unknown together.